Hi, I am Samigdha and I will be solving question number 1 of homework 10. Okay, so we will start with the Poisson process. So now Poisson process can be thought of as the number n t1 t2 as the number of arrivals in the time interval t1 t2 of length t equals to t2 minus t1 is a quantum random variable with parameter lambda t. So thus the probability of n t1 t2 equals to k is equals to e to the power minus lambda t times lambda t to the power k by k factorial, where k is a whole number and t is the difference between t2 minus t1. If the intervals t1, t2 and t3, t4 are non-overlapping, then the random variables and t1, t2 and t3, t4 are independent. So using the points ti, we form the stochastic process xt, which is the n 0 to t. Now, equation 1 is a discrete state staircase function consisting of increasing staircase function with discontinuities at ti. For a specific t, xt is a random variable with parameter lambda t. So the expectation of xt can be written as expectation of n 0 to t, which is lambda t, and expectation of x square t is expectation n square 0 t, which is equals to lambda t plus lambda square plus t square. So now to determine the correlation function Rx x t1 t2, we will use the property B as stated before. So Rx t1 t2 can be written as lambda minimum t1 t2 plus lambda square t1 t2 for both the cases where t1 is greater than equals to t2 and t1 is less than equals to t2. So if we draw the graph of xt, the Poisson process will look like a staircase function. So from the above, we can say that in Poisson process, events occur at random points, but the average rate at which it occurs is constant over time. The mean of a Poisson process is equal to parameter lambda t. This means if we observe the process over a long period of time, the average rate of event will approach lambda t. Okay. So next we move to Poisson increments. So with xt, a Poisson process defined before in part 1 and epsilon is a positive constant, we construct a new process yt, where yt is xt plus epsilon minus xt by epsilon. Now let's find the probability distribution density. Probability yt equals to n by epsilon, which is equals to probability epsilon yt equals to n, which is equals to probability xt plus epsilon minus xt equals to n, which is equals to e to the power minus epsilon into lambda epsilon to the power n by n factorial, where n is the number of arrivals in t and t plus epsilon. So mean can be written as expectation of yt, which is expectation of x plus t plus epsilon minus xt by epsilon, which is 1 by epsilon, expectation of x plus t plus epsilon minus xt, which is 1 by epsilon times epsilon lambda into epsilon, which is lambda. So the mean is a constant lambda. Autocorrelation ry t1 t2 equals to expectation of yt1 yt2, which can be written as lambda square if the modulus of t1 minus t2 is greater than equals to epsilon, and if it is less than epsilon, it is lambda square plus lambda by epsilon minus lambda t1 minus t2 by epsilon square. So if we draw the graph of r t1 minus t2 as, we can see this area equals to lambda, which does not depend on epsilon, frankly, if t1 t2 and r t1. So the above is a result of the memoryless property of the Poisson, which states that the number of events that occur in any given time interval depend only on the length of the interval and not on when the interval starts. Okay. We now go to Poisson impulses. We can define a stochastic process zt as follows. Zt can be written as dxt by dt, which is equals to limit epsilon approaches to 0 yt. So zt can be as impulses at different time intervals. An expectation of zt can be is equals to d by dt expectation of xt, which is equals to lambda. And from equation 6 we can write the autocorrelation function as lambda square plus lambda delta t1 minus t2. Okay. Now, fourth part, semi-random telegraph signal. This stochastic process can be defined as xt equals to 1 when k is even in 0 to t, minus 1 k is odd in 0 to t. So let pk denote the probability that the number of points in the interval 0 to t equals k. Now probability of xt equals to 1 can be written as p0, p2, p4 up to this, which is equals to e to the power minus lambda t cos h lambda t. P probability xt equals to minus 1 can similarly be written as e to the minus lambda t sin h lambda t. So now the expectation of xt can be written as e to the power minus 2 lambda t. Autocorrelation function is given by e to the power minus 2 lambda modulus of t1 minus t2. So this process is called semi-random telegraph signal because its value at x0 equals to 1 at t equals to 0 is not random. That's why it is called semi-random. Now for the part 5, which is the random telegraph signal. Let a be the random variable independent of xt with probability a equals to 1 and probability a equals minus equals to half. We form a new process yt equals to axt. Okay. Mean can be written as expectation of axt, which is equals to 0. Autocorrelation can be written as e to the power minus 2 lambda modulus of t1 minus t2. Okay, so we can see that as t approaches infinity, the process xt and yt have asymptotically equal statistics. It's just that at t equals to 0, this xt is not random. Now random variable. So now the next part, the sixth part, random walk. Random walk is defined as the mathematical model used to describe the movement of a variable that changes randomly over time. The steps are typically independent and identically distributed. So let's consider a simple random walk where each step is equally likely to be in any direction. So we can think of that each step is determined by flipping a coin. That is, if it comes head, the walker takes a step to the right. If it comes tails, the walker takes a step to the left. The direction of each step is determined independently of the direction of the previous steps, which makes the walk a memoryless process. So let the process be x and t. X and t is ks minus n minus ks, where k is the number of head, n minus k is the number of tail, s is the step. X and t is equal to 2k minus ns. So xt equals to x n capital T for nt for small t between nt and n plus 1 t. Okay. So probability of k equals to k can be written as nck p to the power k q to n minus k, where this can be assumed as toss an unfair coin n times the probability that head shows up to k times. P is the probability of head, q is the probability of tails. If it is fair, since we have assumed it's fair in simple random walk, can be written as nck times 1 divided by 2 to the power n. Probability mass function can be written as probability of x and t equals to rs, which is probability of k equals to n plus r by 2, as we can see here, which can be written as n plus r divided by 1 by 2 or n. Now let's introduce yi, which is an IID sequence as follows. At t equals to it, yi is s if it is head, minus s if it is tail. So clearly expectation of yi is 0, expectation of yi square is s square, and expectation of yi yj equals to 0 for I not equals to j. So then xt can be written as summation yi I equals to 1 to n. So expectation of x and t is 0. Expectation of x square and t is n times s square. Autocorrelation can be written as minimum n comma n times s square. Okay, so now we move to the next process, which is the Wiener process. It can be defined as a limiting process of random walk. Wt equals to limiting xt when s approaches 0, t approaches 0, n approaches infinity. Random walk we have expect x square t is ns square. Wiener process we should have the second moment finite, that is non-zero. So limit, if we do it, so the second moment comes around alpha t, which where alpha is a constant. So Wt can be written as limit t approaching 0 and s square by t approaching alpha xt. So now mean can be calculated as Wt, which is 0. Autocovariance is minimum t1 t2 times alpha. Is the limiting value. It depends on the limiting value. Okay.